It's my pleasure to introduce Dr. John Kruschke, who is our morning speaker this morning. He's a provost professor in the Department of Psychological and Brain Sciences at Indiana University. His PhD is in cognitive psychology from UC Berkeley. He's well known for advocating the use of Bayesian methods of data analysis in the psychological sciences, and he's written a very well-received and well-known textbook in Bayesian data analysis. And especially with the emphasis on evaluating evidence, that's the theme of this conference, I thought it would be great to have the Bayesian perspective presented. And I think it's great to have someone who's not in a statistics or math department to give us that perspective as well. So I was delighted when John accepted the invitation to present, and I'm looking forward to his presentation. So please welcome John Kruschke.
Well, thank you all very much. I deeply appreciate the invitation to be here, and I'm glad to see all these people first thing on a Saturday morning. You could be sleeping in, but you're here to hear about Bayes. I'm curious to know, because this is the first time I've been to a US COTS meeting, I'm curious to know how many of you have actually tried to teach some Bayesian in your courses. A subset, but a reasonable number. Interesting. How many of you really don't know much about Bayesian, but are here anyway? Okay, great. Okay, thank you. So in the beginning of the talk, what I'd like to do is, in the process, tell you a little bit about what got me so interested in Bayesian approaches. And so I'm going to start with just this question: why teach Bayesian? And I'm going to show you a series of premises and the conclusion that it's worthwhile to teach Bayesian. And then I'll unpack each of those premises a little bit more. So first, Bayesian is valuable in real applications, and it's sought after by researchers. Second, Bayesian is easy to teach, and in my opinion, easier than Frequentist. And Bayesian clarifies Frequentist ideas, especially if you set them side by side and you see the Bayesian information. It really clarifies, oh, that's what the Frequentist is telling me. It's different than this Bayesian stuff. And these together lead me to this conclusion that it's at least reasonable that Bayesian should be in the curriculum. So now let me unpack these premises a bit. So Bayesian is valuable in real applications. For me, this has been the clincher. What I really do is I'm not primarily a Bayesian educator. I'm primarily a researcher. And I have just found over and over and over that the Bayesian analyses let me do what I need to do when I'm analyzing complex data sets. So just some examples from personal experience. Wednesday, just as I was finalizing this, I haven't changed anything in this talk since Wednesday. I got an email from some colleagues saying, you know, we're doing this study in mate choice, and we have these different strategies people can use in mate choice. Oh, this is mate choice in humans, by the way. We have these strategies people can use, and we look at the proportion of strategies as a function of age. And we see this kind of U-shaped curve in the proportion as a function of age. And what we're trying to do, what our reviewers have told us we need to do, is demonstrate that the dip in the U is actually between the extremes. It really does go down and then go up. Okay. So I thought, oh, well, there are lots of ways you could try to demonstrate that, but here are several from this Bayesian approach. Like, one thing you can do is in the quadratic, if you're going to fit a quadratic curve, find where the nadir of that parabola is, and look at the credible interval on that nadir and show it's clearly between the two endpoints of your x values. Or better yet, if you're really going to get in there, show that the posterior predictive interval on what you're going to predict for the proportions on the one end, on both ends, those are clearly above the posterior predictive interval for what's at the nadir. Okay? And I'll get back to you 2 weeks after I go to this conference. Some work that I've published recently in the journal Law and Human Behavior with an amazing student named Brad Celestin. we've looked at civilian perceptions to police use of force. What we do is we present people with mini vignettes. The civilian did this action, and then the police officer did this other reaction. You have to rate on a slider how appropriate or how acceptable is this police reaction to that civilian action. And it's a slider, it goes from 0 to 100. Now, our primary interest is not just ratings of appropriateness. We're trying to estimate the latent severities of these actions. Just how severe is this civilian action? How severe is that police reaction? And so we're simultaneously estimating regression coefficients and item latent scale values. But not only that, as I've suggested at the end of this last line, these are end-censored data. That is, the sliders very often will be pushed all the way to one end or all the way to the other in these ratings. So all we know is that the respondent wanted to push the slider somewhere over there or somewhere over here. And so we have this nice pile of responses on one end, a smooth distribution in the middle, and then a pile of responses at the other end. That's not very normal. But in Bayesian software, it's completely straightforward to treat those as censored data. We know the data are somewhere over there, somewhere over here. So many examples where I need models for unbalanced designs, designs with empty cells, heterogeneous variances, outliers, so I need heavy tail distributions. I can put in all sorts of customized hierarchical structures. One study I've done just recently, collaborated with, has to do with the neophilic behavior of raccoons. Neophilic behavior, sorry, these polysyllabic jargon. It just means raccoons are curious critters, right? They get into stuff. And so they had these boxes that they'd put out into the woodland, tied to trees, and then they have motion-sensitive cameras. So when any critter comes within the radius of the motion sensor of the camera starts rolling, and you see what animal is there. Question, does it contact this box? Is it inquisitive? Okay. And so they look at the proportion of contact for all these different species that happen to come up in different seasons, and as a function of different baiting, that is it baited or not, and so on. Now, in this situation, there are lots of empty cells because sometimes you don't see a skunk at an unbaited box in winter, but you'll see deer. And so it's a very unbalanced empty cell design. And if you try to do that in traditional approaches, it would just crash. But in a Bayesian world, it's no problem. And this goes on and on and on. Other situations where you look at your data and you realize, oh, I need this kind of trend with this sort of kind of decay function for different items. And it's completely straightforward to put any model you need that actually describes your data in useful ways in a Bayesian framework. So, as I said, all of these are straightforward in Bayesian. And for me, that's what really compels my continued use and fascination with Bayesian methods. But you don't have to take my word for it. Bayesian is sought by researchers. And again, I'll just try to argue for this point through personal experience. Over recent years, I've done 45 workshops with audiences of working professionals and graduate students from academia, in every department across the sun, from economics and education and climate science and biological sciences and cognitive sciences, and keep going through the alphabet. They're all there. Business and industry representatives show up at these workshops. People studying retail sales, charitable giving. They're trying to model the characteristics of who's going to give and who not. Food production. People showing up, they're interested, for example, in how to make better bacteria for cheese so that the cheese is more stable and so on. In government, I've given workshops at the FAA where they're studying human factors, and at the FDA where, among other things, they're studying survival analysis. And they're all interested in these Bayesian methods, presumably because it's really useful. Bayesian is easy to teach, and I would say easier than Frequentist. In fact, I was initially driven to Bayesian by aversion to teaching Frequentist. For years and years, I've taught Frequentist stats, and I try so hard to explain the p-value and the sampling distributions. And then we'd get to the section in ANOVA where I have to justify corrections for multiple tests. And then I have to talk about things like the Tukey HSD. And have you done the Tukey HSD? Show of hands. HSD? Tukey HSD? What does HSD stand for? Honestly, significantly different. Okay, if honest, be honest. Do you really want to do all those comparisons? Come on, you know you do. You know you really want to do those, don't you? Okay. And I've read so many manuscripts, that is, manuscripts submitted to scientific journals, in which the authors go through these kind of gymnastic contortions to try to justify why they only want to do these 3 tests. And curiously, the p-values of those 3 are like 0.04, And it's like, it's obvious, really, you should be looking at a lot of other tests, but no, they're going to rationalize, right? No, just these 3. Or they'll take what's clearly one experiment design, and they'll split it into 2 experiments. This part of the design is experiment 1. This part of the design, that's experiment 2. And therefore, when we're doing our corrections for multiple tests, we only have to correct over these corrections that are for these tests that are in experiment 1, and not factor in all these other tests that are in experiment 2. So it's having to teach things like that just bothered me, and also that you know so well this kind of inverse logic of the p-value. And I've taught Frequentist and Bayesian courses separately for years. So let me tell you a tale of 2 courses. These are courses I teach at the introductory graduate student level, first-year graduate students from across the university. Okay. Both courses begin the same way. I cover fundamental concepts of data and models. You're going to use a model to describe your data. Both courses conclude, the last half or more, is the generalized linear model. So I cover the various dependent variable types. Under metric dependent variables, we go through multiple linear regression and all the various ANOVA style models. We look at logistic regression, and then under nominal dependent variables, we look at, of course, multinomial regression or conditional logistic regression. And we go on to ordered probit models. And then for count data, we look at Poisson or negative binomial models and so on. So that's the same in both courses. What's different? Well, all the framework you're going to use to consider all those models. So of course in the Frequentist class, I have to cover sampling distributions and p-values and confidence intervals and the testing intentions and stopping intentions. Why did your n come out to be 122? Did you really plan to have 122 in advance? Okay. And in the Bayesian world, in the Bayesian class, I teach the Bayesian reallocation of credibility across parameter values. I'll tell you more about that soon. And then I cover the Markov chain Monte Carlo methods for representing those distributions. And just from personal experience, the right column is so much smoother, and students just get it. The left column I've worked on, and I think the students actually get it, but even after they get it, they look at me like, really? That's how science works? Okay. All right, and then this other premise. Bayesian clarifies frequentist ideas. This has actually come up in conversation spontaneously, and I was so glad to have this slide in the talk because it echoed exactly what I've heard from other people. How often have you told students, this is a quote from an instructor, the p-value is not the probability of the null hypothesis? Okay? And then the student says, well then what is? And you have to provide a Bayesian answer. There's a Bayesian approach to putting actual probabilities on null and alternative hypotheses. And so you can point to the Bayesian answer, and then the student will get this aha. By pointing out the distinction, they say, oh, aha, the p-value is about a distribution of imaginary data. And it really focuses them on that distinction. Or the instructor can say, the 95% confidence interval is not the range of most possible values, of most probable values. And the student goes, really? Well, what is? And you provide a Bayesian answer, a Bayesian posterior distribution. That shows you the distribution of most probable values. And the student goes, oh. And then through contrast realizes, oh, the confidence interval is about not rejected values. So putting them side by side really helps clarify the information. So just to recap this series of premises and the suggested implication that Bayesian should be in the curriculum. So then we get to the question, how? How can we include Bayesian in our courses? Small font, sorry. But there's a lot of little options which get rejected. Option number 1, let's replace the standalone frequentist course, right? Let's get the frequentist course out of there. Chuck it. Well, no, the frequentist methods are entrenched, and they really do address the issue of error rates. They really do address this issue of error rates. If you want to control error, you got to go the frequentist route. Okay, well, what about adding an optional standalone Bayesian course? Well, no, students won't take it and instructors won't prep it. Okay? How many of you would just go out there and prep a brand new course in Bayesian? Even the enthusiasts find that very daunting. And I say students won't take it if it's optional and their schedule's already full, they're not going to take it. Now, I have done this, okay? And every year I get 40 students in that room from all across campus. And so in that sense, it works. And I'm a real enthusiast, so I've prepped the course. But if you look at that course versus all the frequentist courses taken, my course is just a tiny sliver of what students are doing. So just having an optional standalone course won't really do the job. How about a required standalone Bayesian course? I think that would be terrific. But no, it's not going to be required anytime soon. So that's unrealistic. Well, then any separate course? Should you just have a separate Bayesian course, separate from frequentist? And no, maybe that's just not the best way to go. Maybe the juxtaposition inside one course actually can actually help clarify both. So I'm going to take that and run with it a bit. Let's inject Bayesian and frequentist into existing courses. So how? How to inject Bayesian and frequentist into existing courses? Well, one option is, what we need is a module that is self-contained, so it minimizes teacher prep. Yay, all in favor of minimizing teacher prep? Yay. A module that has a complete tutorial explaining Bayesian and frequentist analyses, so the instructor doesn't have to go do a lot of background self-education. It has interactive software that's browser-based. You don't have to install software on your computer. It has some interactive exercises, and it has clear learning objectives and assessment. It'd be nice to have that. And when Alan invited me to give this talk, I was thinking, something like this has been on my mind for a long time. So I'm going to take the plunge. I'm going to take today as my deadline for getting something like this at least unveiled. Okay. So I've been working really hard on a new Shiny app to at least get this started. And here I say it's accomplished. That might be a little bit of an overselling. It's there. It's ready for revision. So what I'd like to do is give you an overview of the Shiny app. It's available on my website. I think the hardest thing about learning this particular branch of Bayesian statistics is learning how to spell that guy's last name. It's and you try to type it into Google, and it gives you, like former leaders of the Soviet Union and. Anyway, it's on my webpage. You can get to it there. So here's the screen layout of the app, the basic structure of the screen layout. Notice on the left side, there's where you specify data. And then there are two columns. There's a frequentist column and a Bayesian column. Okay, so side by side, yay. But then there are also two rows in the app. There's a row for an estimate with uncertainty, and then there's a row for a null hypothesis test. So then you might be asking, why do you have those two rows in there? Why teach hypothesis testing and estimation with uncertainty? Well, they have different goals. Hypothesis testing seeks a decision regarding a specific hypothesis. That's what it's about. Can you decide about this hypothesis? But estimation with uncertainty seeks a description of data with some degree of precision, quantified precision on that description. Okay? Different goals, different information. Hypothesis testing is traditional and ubiquitous, so we can't just kind of pretend it's not there. But of course it does have issues. The cognitive trap of black and white thinking, that was described yesterday as bright line thinking. And estimation with uncertainty is encouraged by best practices, as we've heard a lot now from yesterday's speakers, the ASA statement and the American Statistician special issue going beyond 0.05. So that means that both of these approaches are perhaps important. But why teach them? Well, again, the juxtaposition can clarify both. And estimation with uncertainty is, again, in my opinion, more intuitive and easier to teach. Indeed, the app's default view has no hypothesis tests. Yay! So the app, you pull up the app, you invoke the app, it's got the two columns. What shows up is the estimation row. There's nothing in the hypothesis testing row. Okay? And to me, that alone was a little mini revelation. As I was setting up the app, by default, I had everything there. And then I realized, oh, wait a minute. To do a hypothesis test, you have to specify what hypotheses you're testing. And by default, you're not testing anything. Oh, by default, I should leave that row blank. And then it's like this weight off my shoulders. Okay. Nevertheless, though, in the app, you have results from all four of those cells simultaneously displayed. And so, in particular, you can see side by side what does the frequentist analysis provide and what does the Bayesian analysis provide, either in the row for estimation or in the row for hypothesis testing. And of course, you can look at the comparison between the two rows. Oh, what is the information that estimation provides? What is the information that hypothesis testing provides? And just having them all available at once, it's a busy array, but it gives it the opportunity to really clearly see the distinction between the information provided. Okay, in the app, there are lots of controls, lots of sliders. There are controls, of course, in the data. You've got to specify where your data are. There are sliders that specify, like in the lower left here, what are your null hypotheses? What's the value of the null value for mu, the mean, for example? Okay. Over in the Bayesian column, what are your assumptions about the prior distributions? So there are all sorts of sliders for setting up your assumptions to do the analysis. Now, what's really neat then is you can observe all the influences simultaneously. So you change your data, you can see what that does to all the results simultaneously. You change your null hypothesis tests, you can see what that does to all the output simultaneously. You change your priors in the Bayesian, what does that do to all this information? But what's also neat about this kind of setup is the sliders point you to exactly the information you need from the real world when you're trying to do an analysis. Okay, so you set up, there's some story problem, some exercise, or even some real-world analysis where the story problem or the real world provides this vast array of information. And then you say to the student, okay, go analyze it. Go. What they need to do is extract from the world the relevant bits of information to set up the analysis. And the sliders basically focus their attention on exactly what's needed. Oh, okay, if I'm going to do this frequentist analysis, oh yeah, I've got to think about what is the null value and so on. What are my stopping intentions and all that? And the structure of the app, and this applies not only to this app, but to all the many apps that many of you have created, it sets up a really natural structure to think about the intended learning outcomes. So one category of learning outcomes is for, as I say here, is for in-depth understanding of frequentist and Bayesian analyses and their interrelation. And it's achieved by interactively manipulating the sliders and watching what happens and figuring out why. And there's a finite, although it's a large number, there's a finite number of these arrows from sliders to what happens in the analysis. And each of those arrows is a potential assessment question as well. And then the other category of learning outcomes is the connection of the sliders to the outside world. And as it says here, you should have an in-depth understanding of how to apply to real situations. And that's achieved interactively by translating situation to a setting of the sliders. And the app makes explicit what needs to be found. So then how do you assess those learning outcomes? Well, you should be able to predict the qualitative effect of every slider and button on the results in every cell of the table and explain why. And how do you assess that other category of outcome? Well, you should be able to set the sliders appropriately to reflect real-world scenarios and explain why. So that's your overview. In my remaining time, I'd like to give you some more details. There is, with this app, an extensive online tutorial. It's big and growing. It has a dynamic table of contents on the left. So as you read through the tutorial, the table of contents shows you where you are. You can click in the table of contents to go directly to any point in the tutorial. The tutorial is replete with try it exercises, which basically has you explore, put the sliders here and look at what happens over there. So, a tour of this shiny app. As you might have guessed, there's an enormous amount of information in the Shiny app. I don't have time to go through the whole thing. I prepared slides to go through the whole thing. There's no way I can possibly get through it. But what I will do is go through kind of the beginning of it and then jump to the end. So the ordering of topics. Oh, first off, this is the display of the app with all of its bells and whistles. Okay, there's a lot there, but if you step through it, scaffold through it, it's actually not too bad. So in the tutorial, you start off with data. That's why we're here at all. It all starts with data. So we start with the data. We move over to the analysis, which basically is the model. What kind of description of data are we going to use? Then we move over to frequentist estimation. From there, we go to Bayesian estimation, and then down to Bayesian hypothesis testing, then over to frequentist hypothesis testing, and then back up to, finally, frequentist confidence intervals. As I thought about it, this, I think, is actually the uniquely best way to scaffold through the topics. If you want to talk to me about that, please do. But there's actually, I think, very strong reasons to do it in this order. So let me just now go through these. So first, the data section. The way I've set up the app here is, rather than the user entering their own data, I've set up so there's a kind of a constrained possibilities of the data. So there's one slider for where the mean is, one slider for setting up the standard deviation, and one slider for the sample size. Let's zoom in a bit just on that data column. And the first triad exercise simply says, oh, move those sliders around and look at what happens to the histogram of the data. And the obvious things happen, as you shift the mean up, the histogram goes higher, and they make the standard deviation smaller and the histogram gets narrower. Increase n and the histogram smooths out. Okay, but that's the first triad exercise. Then we go on to the model. And for these data, the model I'm going to use is just a normal distribution with parameters mu and sigma. Now, this notion of model is utterly fundamental to a Bayesian approach, and I would argue to statistical analysis in general, once you get up into applied research. And so I take some pains to give my students, and in the tutorial, at least some basic intuition regarding what the heck a model is. And as it says here, a model is a data-generating machine with control knobs called parameters. And perhaps the simplest example I can think of is a bathroom shower head. Okay? A bathroom shower head is a data-generating machine with control knobs. What are the data? Well, you can think of these water droplets spewing out of the shower head as little data points. And, they fall on the floor. And now you've got this pile of data on the floor. Okay? And you've got control knobs. You've got a little swivel, which you can call mu, because, we like Greek. And so, hey, mu, that's the swivel. And there's a dispersion control. We'll call that sigma. And it's very intuitive to say, oh, yeah, we've got this data-generating machine. Okay? And it has these two control knobs. And, in statistics, instead of calling them control knobs, they call them parameters. Okay. You could also say, oh, there's a data-generating machine. It's a licorice factory. It's a licorice factory, and this licorice factory has control knobs. The knobs control, how long the piece of licorice is and, how thick the piece of licorice is. And so it's actually a very intuitive concept. And then, oh yeah, by the way, we can put a mathematical formula on the shape of this data distribution generated by the machine, but the math isn't the important part. The math is that you understand what's important is that there's this thing called a distribution. It's a model of data. It has a certain shape, and we have control knobs called parameters. Once you understand that, then you realize, oh, I'm going to understand the data in terms of a machine that mimics the data and in terms of the settings of the control knobs that mimic the data. Okay. I've spent a few minutes on that because the Bayesian approach relies on this notion of model. And I'm just trying to illustrate that you can explain the notion of model pretty much math-free, or at least with math strongly de-emphasized. So then I'll move on to frequentist point estimation. And here I just have some pictures. We've got the normal distribution. That's the machine. That's the shape of data that would be generated by the machine. The gold histogram, those are our observed data. And we're just going to change the settings of the parameters, change the settings of those control knobs until the machine kind of mimics the data, right? That's how we're going to estimate these parameters. And there's a triad exercise. You change the nature of the data and then look at the estimates of the parameters and find, oh, yeah, those, when the parameters are set over there, it kind of describes the data reasonably well. Okay, I'm going to skip through that quickly because I know this is what you're all waiting for. No, I know you're really waiting for 9:30 to come, but I can't make that happen faster. So let me take a few moments to talk about Bayesian estimation. It may have been a while since many of you have gone through Bayesian ideas. Some of you perhaps maybe haven't ever even been exposed to Bayesian ideas. I don't know. So at the last moment, I decided, gee, I really should insert a quick intro to Bayesian estimation. So I grabbed a few slides from other presentations and stuck them in here. Here we go. There are two foundational ideas of Bayesian reasoning. You can explain Bayesian reasoning on the elevator between floors by saying these two things. Bayesian reasoning is reallocation of credibility across possibilities. And in data analysis, the possibilities are parameter values in a mathematical model of data. Okay, any questions? Well, if you unpack these two things, then it's a terrific summary. So let me unpack them. First, Bayesian reasoning is reallocation of credibility across possibilities. This is completely intuitive. Sherlock Holmes used this kind of reasoning all the time. So here, for example, is a quote from Sherlock. "How often have I said to you that when you've eliminated the impossible, whatever remains, however improbable, must be the truth?" Well, what is Sherlock doing here? He's going into an investigation of a crime, say. And what I've got here in this graph across the horizontal axis are 4 suspects, cleverly named A, B, C, and D. Okay, and these are the 4 suspects for this crime. What's being plotted on the vertical axis is the credibility of the hypothesis that each suspect did it. So here we're assuming the suspects are independent. There are no conspiracies of suspects. So the vertical blue bar over suspect A, that's the credibility of this notion that A did it. That's relatively large in this case because, Sherlock thinks, A was nearby, A had a motive, it could have been A. Then there's suspect D over on the right. Suspect D is possible, but there's a lower initial credibility in that hypothesis. I'm using the word credibility because it's an English sort of everyday synonym for the meaning of probability in a Bayesian world. So that vertical axis is actually probability. Now, the top of that graph is marked prior. because that's what Sherlock believes going into the investigation. Those are the prior beliefs. So suppose Sherlock does some detecting and finds that suspect A is impossible. Suspect A has an airtight alibi. What do you then do? You reallocate credibility to the remaining possibilities. You reallocate credibility across possibilities. And that becomes your prior distribution for subsequent investigation. So now, suppose Sherlock finds that suspect B is impossible. Okay, you reallocate credibility to the remaining possibilities. And suppose now you find, oh, suspect C is also impossible. Well, whatever remains, no matter how improbable it was at the beginning, must be the truth. Okay, so that's Sherlock being Bayesian. What does that have to do with data analysis? In data analysis, the possibilities are parameter values in a mathematical model of data. So, I'm going to show you just a really, really simple model of data to map it onto what Sherlock did. So let's consider the tendency of a coin to come up heads. And we'll consider data values here where y, that's the thing you're trying to predict, the dependent variable, y is 1 for heads and it's 0 for tails. Now, how many of you in here care about heads and tails? Show of hands. Okay. So obviously, we use this in place of something people do care about, any kind of dichotomous data. Maybe you're looking at the proportion of females in a species of birds. You're an ornithologist. Or the proportion of left-handers in a group of people. Or the probability of getting a certain question correct on a statistics examination. Okay. But we're just going to go with heads and tails. Now, the tendency for heads is the value of a parameter. We're going to call that parameter theta. And mathematically, you can write it down this way to make mathematically obscure a very simple idea. Theta is the probability of heads. How do you write that down? You say the probability that y equals 1, given the value of theta, is the value of theta. So if theta is 0.7, the probability of heads is 0.7. Okay, so we're going to be Sherlock now. We're going to collect data. That is, we're going to flip the coin. We're going to collect data. And we're now going to infer what theta done it. Okay? What theta done it. So we're going to go into our investigation with a collection of possible theta values. Here, just to make the analogy clearer, I'm putting up 11 candidate theta values. Theta could be 0, 0.1, 0.2, 0.3, all the way up to 0.9 and 1.0. Of course, theta has to be between 0 and 1. And here, just to be uncontroversial, I'm putting equal credibility on all the 11 possibilities. Okay? So, those are the 11 suspects for this crime. And we're going to go and collect some data, collect some evidence. Suppose we flip the coin and we find heads. So this annotation there is y equals 1, which means so far we have 1 head and 0 tails. We reallocate credibility across the possible values of theta. And if you go through the math, it looks like that. Intuitively, what's happened? Well, we got a head, and therefore higher theta values should be more credible. Higher theta values are consistent with getting a head. Notice in particular, though, look at 0, a theta of 0. The credibility of 0 has gone to 0. It's now impossible. Because if theta were 0, you'd never get a head. We did get a head. Okay? That becomes the prior for subsequent investigation. Suppose we flip the coin again. Oh, now we get tails. So for this flip, y is 0. We now have a total of 1 head and 1 tail. We've now reallocated credibility across the possibilities. And intuitively, what's going on there? Oh, the most credible value of theta is 0.5, because we've seen 50% heads. But notice also here, a theta of 1 has been eliminated. Theta couldn't be 1 because we've observed a tail. So we're just reallocating credibility across the possibilities. And we keep going. Okay, this becomes the prior for subsequent data. We collect a third flip. Perhaps now we've got another head, so we have two heads and one tail. And you can see the peak of the distribution is now centering around 2/3. Okay. And that's Bayesian estimation. That's Bayesian analysis right there. That's 90% of Bayesian analysis. The rest is just details. Okay. Everything you want to know, you just read off that posterior distribution. So you want to know what are the most credible values? Oh, there they are. You just look. You can summarize those distributions. You can summarize where's the mode, what's the most credible value. You can summarize the spread. How far do you have to go to cover 95% of that posterior distribution? And so on. And of course, in this whole approach, I never mentioned a sampling distribution. Okay? I never mentioned some hypothetical value from which we're going to draw simulated samples and come up with a sampling distribution. It's just not there. Okay, so that was my little digression into Bayesian estimation. Back to the app. The app is not flipping coins. The app is it's using a normal distribution. So in that Bayesian column, there's a section for specifying the prior, and then a section that shows you the posterior. Zooming in on the prior, here's where we set the prior on mu, the mean of the normal. And you can adjust the center of that prior distribution. You can adjust how spread out it is. It defaults to a very spread out prior, again, because that's uncontroversial. You're not importing any prior biases into your analysis. But you can play with it, right? You can make that prior very specific and see what that does. Here's the graph of the posterior distribution. It's annotated, and of course the tutorial explains all the notation there. So I don't assume people, students know, oh, P of mu given D, what is all this crazy notation? That's all explained. But here, what's marked is the mode of the distribution. That is the most probable, the most credible parameter value. And the distribution, the spread of the distribution, is summarized by the 95% HDI. What's that? That's the highest density interval, HDI. It contains the 95% most probable parameter values. It's just a summary of the distribution. It's simply saying, everything inside that interval has higher probability than anything outside the interval, and that interval covers 95% of the distribution. It marks the 95% most credible values. It's just a summary. And so there are lots of triad exercises. You can manipulate the sliders for the data, see what that does to the posterior distribution. You notice all the intuitively appropriate things. For example, the posterior tracks the data, so you move the mean of the data up, the posterior on mu goes up, and so on. You also notice that as you increase the sample size, the posteriors get narrower. You get a more precise estimate. You're more certain about the most credible value of the parameter. And of course, there are triad exercises where you manipulate the prior to see what effect that has on the posterior. And one of the cool things you notice is that, most of the time, the prior doesn't have much of an effect on the posterior. As long as the prior is reasonably vague, the posterior is virtually unchanged. And it's only when you have very strongly informed priors that it has much of an influence on the posterior. So I know a lot of people might be really concerned about capricious priors. Like, oh, it's Saturday morning. It is Saturday morning, isn't it? It's Saturday morning. I'm feeling pretty good. I've had enough coffee. I'm going to set a really good prior. I mean, you can't do that. In scientific research, you can't just throw in some capricious prior. Your prior has to be justified to the audience of the analysis. And what this shows you is that if you're going to have a justifiable skeptical prior, it's fine. Don't worry. Okay, I'm coming close to the end here, so I just want to tell you one more thing before I conclude. As I mentioned, when the app is invoked, it doesn't show you any hypothesis tests. Look at that lower row. It's blank. There's a wonderful book that was written, first came out in the 90s, edited by Lisa Harlow and others. It was called, What If There Were No Significance Tests? Hence the title across the slide. What if there were no significance tests? What would the world look like? It would look like this. It's a beautiful world. What should you believe about your parameter values? There it is. Oh. But I know, sometimes you want to do a hypothesis test. And so what you do is you click, where I've highlighted in red, you click a button for which hypothesis test you want to do. And then it populates that section of the app. And it goes through Bayesian hypothesis testing, which I don't have time to go through. It moves on to frequentist hypothesis testing. There's a whole attempt to describe in the tutorial what the heck a sampling distribution is by starting with a picture of a null hypothesis and illustrating all the samples and then making a sampling distribution. So I go through the effort to explain that. And then this is what gets displayed in the frequentist world, in the frequentist cell of the app. It shows the p-value. And because p-values, despite what we heard yesterday about, don't use significance, that term, that's the way p-values are used. So if you're trying to teach students, I think you still have to at least teach them what that means, even while you're telling them not to do that. So the alpha is on display. One of the things you'll notice is here I'm doing two tests. I'm testing both mu and sigma. And so the alpha is corrected for these two tests. And the p-values are marked with the star or ns, depending on if they fall below alpha and so on. So that's all highlighted and explained. There are lots of triad exercises. You can manipulate the data, watch the effect on the p-values. You can select which tests you're going to do and look at the effect on alpha and the pretty star or the ugly ns. Here's something that I've stuck in, which expresses a pet peeve I've had all these years, and that is the assumption of fixed n. Every sampling distribution under the sun assumes fixed n. Okay? Like the one I just showed you a minute ago. This one. You've got your hypothesis, and you generate samples, and every sample has the same sample size. I have almost never done research with a fixed n in advance. Okay? And there are some people who say, oh, the only way you can do proper research is by fixing n in advance. Well, why is that? Because it's good research? No. Because if you want to look up a p-value based on fixed n, your data collection has to have fixed n. How do I collect data? Well, there are lots of different ways. So for example, you can put a survey on crowdsourced data collection like Amazon Mechanical Turk. So you say, okay, I'm going to put out 200 opportunities to take this survey. And I know I've got like a minute, right? Yeah. So I put out these 200 surveys, and I get 200 people have filled it out. Well, some of those people are bots. Some of those people are just clicking at random to get through it as fast as they can and, get their $1.50. And so you've got to put in a lot of catch questions. A lot of catch questions that say, oh, for this question, move the slider all the way to the right. Or on this question, please check the box for somewhat disagree. Okay. And then you have to go through the data, and the people who have failed those check questions, you exclude. So what's your N? Well, N is, 148. It's a random number. It's a random number. So we really should be sampling to mimic the way the data are actually collected. That's what this is for. What would have happened if the null hypothesis were true and I collected data the way I actually collected my data? That's what a null hypothesis is. And that's what a sampling distribution is. It's a distribution of data I would have collected the way I collected my data if the null hypothesis were true. Okay, so what I do is I've got this version of random n. It's a Poisson distribution on n, and it computes a p-value if you had a Poisson distribution on n, and it's a different p-value. Okay, so that's in there for your pleasure. Okay, so just to recap, because I'm out of time here. Although it is a busy display, I think it can be really useful both as a learner and as a teacher, because you get to compare the information side by side. You really get to see, oh, the Bayesian information is different than the frequentist information. Oh, the hypothesis testing information really is different than the estimation information. So you get to compare those things side by side. And not only do you get to see what the sliders influence, you get to see what the sliders don't influence. And you see, oh, wait a minute. When I change which tests I'm doing, that changes my alpha value, but it doesn't change anything over on the Bayesian side. And when you change the priors, oh, that doesn't change anything on the frequentist side. And so learning what the sliders don't do is also really valuable, I think, to students. And then finally, just to reprise the learning outcomes, these internal arrows say you should be able to predict the qualitative effect of every slider and button on the results of every cell and explain why. And then those external arrows, be able to set the sliders appropriately to reflect real-world scenarios and explain why. So, as I said, this is my first kind of version 0.9. Okay. And what I'd like to hear from you in the breakout session, among other things, is how to improve the app. So would it help to have guidelines for where and how to insert this into existing classes? That's the goal, that you could just take this and put it into a class. Would it help to have guidelines? How about submodules with videos? Yay, videos. Would it help to have some specific exercise sets and quiz banks? Should there be a simpler one-parameter version so you don't have all these sliders from U and sigma? The peril of a one-parameter version is I can't put in corrections for multiple tests, but maybe it would help. What about software that allows inserting user data? There are pros and cons of doing that. So I hope you can discuss that at the breakout session. And then the $64 million question. Has there been inflation? Is it more than that now? The national debt-sized question: how to get teachers to adopt the app. Well, do I need more arguments in favor of Bayesian? Demos of how intuitive and easy it is to use, examples of how the juxtaposition clarifies both. More arguments against frequentist? And everybody loves that. No, everybody hates that, so I won't do that. Evidence of efficaciousness. Would it help to go do a study and show, well, when you teach people this, they tend to learn more than when you don't teach it to them? I know but would it actually help if a study was done right to show that this was efficacious? I don't know. How about endorsement by agencies, societies, and leading instructors? I'd love to have leading instructors endorse this. So we can discuss that. So again, the tutorial and the app are online at that weird spelling website. I hope you'll at least check it out, get a reaction to it one way or the other, and whether you like it or don't, let me know what you think. I really appreciate it. Again, I really appreciate your coming here early. Thanks.
Thank you very much. How about one quick question? We have a question. Anyone dying to ask a question? You'll have a chance at the breakout session, obviously, to question and discuss. Yes, please.
I have one quick question that other people might be wondering, and I just haven't gone to the website yet. This is a test for mu, obviously. Not all hypothesis tests are for mu. But do you have it set up so that you can test, say, a proportion? Population proportion, or do other types? I know it's your version 0.9, so maybe the answer is no, but.
Right, no, great question. So this app is for just a particular set of data that is, if you will, one group of metric data. Okay, and so we're going to describe those data with a normal distribution. That's what this app starts with. So if you have different kind of data, dichotomous data, and you'd like to describe the proportion, well, that's different data, a different model, different app. What would be great is to have a whole catalog of these things. So here's the app for proportions, here's the app for one group of metric values, here's the app for linear regression. Of course, the more parameters you put in, this gets incredibly densely packed. Right.
Cut off the questions there. Thank you again very much.